Next up, let's take a look at some alkenes and check out their stability. So one example we can think of is a cis alkene versus a trans alkene. And in this cis one, we can see that we have some steric hindrance, whereas in the trans, we do not. And so overall, trans is going to be more stable than cis. And then the other factor, and even so more the bigger factor, is the level of substitution we have in our alkenes. And so basically, the more substituted they are, the more stable they are. So for example, if you have an alkene that has 4 non-hydrogen, we call this tetrasubstituted. And so that'll be the most stable. With only 3 non-hydrogens, so it'll be tri-substituted. Next, stable. And then we've got a whole grouping of di-substituted. Right. As we said previously, the trans is going to be more stable than the cis, but actually more stable than either one of these is the geminal. And that's when we have both of our substituents on the same side. A little bit not what you would expect, but that's what's shown experimentally. And then finally, the mono-substituted is the least stable. And so again, when we go from left to right here, we get more stable. The why behind all of this, we're just going to say it's hyperconjugation. It's beyond the scope of this course. So we'll just focus on what is the more stable rather than really getting into the nitty-gritty of why. And then, of course, you have to take in other factors as well. Something, for example, is like ring strain. Ring strain can make alkenes less stable. So, for example, if you did cyclopropene, if you think about the bond angles involved in this alkene, it's not going to be very stable at all. And even cyclohexene is going to be less stable than a regular alkene would be. So just some things to keep in mind when it comes to alkenes.